Okay, um, let's start. So we are in week 10 of the class. Um, and this week and the next 2 weeks, so that's the next 3 weeks, we will be covering discrete optimization. So we have done linear programming. We have covered what one thinks of as the most important ideas that you need for LPs. And this will naturally take us towards discrete optimization. And again, my goal will be in about 3 weeks, which is about, I guess we get about 12 hours contact time for this. I will try to cover some of the key ideas in discrete optimization. Okay, again, it will be a much broader topic than what I cover, but I will try to talk about the key ideas. Okay, so this week, what we'll do is, so today we will discuss essentially integer programming. Okay, or also some people like to call this discrete optimization. The word programming is not as popular these days for LPs and IPs simply because programming is more associated with computers. But integer programming or discrete optimization, and our goal for this week's mainly will be uh, to focus on formulations. Okay, so formulating IPs itself is an interesting tool. It's an interesting art. There are ideas that there which are non-trivial. So we will talk about that for this week, and next 2 weeks, the following 2 weeks, I will basically discuss more methods. How have people conceived solving integer programs? Okay, and what are some of the key ideas? Okay. Okay, so let's get started. So a quick reminder, what's a linear program? So a linear program, let's say I look at a standard form LP, it's basically AX equal to B, X non-negative. That's my LP, which you are now well versed with, and we know how to solve. Okay. Okay. So the natural extension of this is what is called integer linear program. Integer linear program, or in short, I'll call it IP, integer programming, which is to minimize C transpose X subject to AX equal to B, X non-negative, and I put one additional constraint which says that X has to be integer valued. Okay, so you have a vector X, this has to be an integer vector. Basically, every coordinate has to be an integer entry. Okay, that's all. This one additional constraint. Okay. So again, ILP simply means it's an integer linear program. In short form, integer programming, IPs. Okay, I'll also use IPs or ILPs. There are linear constraints and integer variables. Okay. Okay. Now, a class of these problems is what are called 0-1 linear programs. Okay. A subclass, which is basically to minimize C transpose X subject to, let's say, AX equal to B, let's say X non-negative, but instead of X non-negative, I'm going to say X takes values in 0, 1, n. Okay. And again, I can have AX equal to B, but we can always have inequality constraints too. Okay. So we can obviously, we can have constraints like AX greater than equal to B, or AX greater than equal to B, or less than equal to, it really doesn't matter. Okay. We can have any type of linear inequality constraints, but we have essentially X taking only binary values. So X takes only every vector X is a binary vector. Okay, so this is a subclass of integer linear programs. Okay, again, there are some linear constraints and there are uh, binary variables. Okay, okay, this is also called combinatorial optimization. Okay, where you're optimizing over combinatorial spaces. So what are combinatorial objects? Essentially, when you are having this sort of subset of the hypercube. Okay, extreme points of the hypercube. Okay, the final, the most general class of these problems is what are called mixed integer linear programs. Mixed integer linear programs, where you have two sets of variables. Let's say you've got sets C transpose X plus D transpose Y. So there are two variables X and Y. I've got constraints. Maybe I've got constraints of the form AX plus BY equal to B. X is non-negative, Y is non-negative, and only Y are integers. Okay. So why is this a mixed integer linear program? X can take values in Rn plus, while Y has to be integers. Okay, so some of the variables are integers, some of the variables need not be integers. You are allowed to be um, uh, any real number. Okay, so that's a mixed integer linear program. Okay, and of course, like we have Rn and Rn plus. Okay, we'll use the notation sometimes Zn. Basically, what is this? This is essentially the Cartesian product of integers. Okay, n times. So Z is basically the set of integer vectors in n dimensions. Okay, and similarly, Zn plus is simply non-negative integer vectors. Okay, so sometimes I'll use Zn and Zn plus. Okay, okay. So is a general definition, and again, you can have inequality constraints. You can have equality constraints. It doesn't matter. Okay, so is a general definition of the classes of problems clear? Of course, everything here is linear in the sense that there are only linear objects. The functions that show up in the objective or in the constraints are linear except for the integrality restrictions. Okay, anything which says something is integer is not a linear constraint. Okay, okay. It turns out this class of problems is extremely powerful in modeling many problems which are of interest. Okay, and over the last 50 to 100 years, many interesting ideas have been proposed and models have been developed to solve IPs and integer linear programs. Okay, and it's a very active area of research, and uh, it turns out to actually be very useful because in many applications you want to model binary actions or integer actions, and we will see examples of it. Okay, okay. So, any questions with the definitions of the classes of problems? Yes, yes. So when I say 0, 1, n, thank you. It's basically, so for example, this is 0, 1, 2. The only the sorry, this is 0, 1, 3. Only the extreme. So everywhere. So for example, what is 0, 1, 3? 0, 1, 3 is basically 0, 0, 0, 0, 0, 1 up to 1, 1, 1. So there are 8 vectors in the set. Okay. Okay. So when I say 0, 1, n, it means the Cartesian product of 0, 1 into 0, 1 into 0, 1. Okay. Okay. Is the definitions clear of the problems classes? Okay. Of course, you can look at quadratic problems, nonlinear problems, and of course, people have studied all these versions: quadratic integer programs, nonlinear integer programs. We won't. I will somewhere along the way. I'll introduce some quadratic integer programs. But again, these are very active areas of research. Okay. Okay. So let's first talk about why should one even care about integrality? Why is this important? Why is it relevant? What can you actually model with this? If you have algorithms solve IPs, what can you do? Okay. By the way, okay. So just to give you a sense, there are excellent solvers, both academic and commercial, to solve integer linear programs. So there is Gurobi, there is Cplex. Okay. There are many such solvers out there. So all these are solvers which have been developed to solve IPs, okay, integer programs. Okay. And they have algorithms which will solve integer programs, and you can find them. Okay. And they're very useful. Okay. Okay. So let's first talk about what can you model uh, with IPs. Okay. So I'm going to go through several ideas of modeling just to show you the power of modeling with IPs. Okay. So the first thing, obvious one, is you can model binary decisions, which is the most obvious thing. That in many problems, you're trying to model either doing something or not doing something, buying a stock or not buying a stock. Okay. Producing an item or not producing an item. Okay. assigning a student to a project or not assigning a student to a project. That's a binary decision. You're not wanting to send 20% of the student to work on a project and 80% of the student not to work on the project. Okay. You don't want 20% of a patient to get health, no, 0.2% getting medicine and 80% of the patient not getting medicine. Okay. So there are very naturally problems of assignment type or binary choices where you have to allot something to a particular option. So anytime you have that, you will have a binary decision variable where x will be 1 if you choose some option, and the option will depend on the problem context. Okay. And 0 if you do not choose the option. Okay. Whatever the option might mean in your particular context. Okay. And you have to make this choice. It's a decision you have to make. Okay. So the simplest one that we have seen is 0, 1 knapsack. Okay. We have seen this problem before. Okay. What is knapsack? I have many items. Okay. I have different items. Each of them has a, let's say, a weight, W1, let's say W2, W3, W4, Wn. So this is weight of each item. There's a profit for taking it. So if I put an item in a knapsack, I get some profit. Let's call it P1, P2, P3, P4, Pn. And what I want to do is, I've got a total large knapsack of weight W. I cannot exceed this total weight. So I have to figure out in this knapsack which items I put in. So I need to figure out, do I want to put in items 1 and 3 and let's say the last one, so that the total weight does not exceed capital W, and I want to maximize profits. Okay. So the problem there would be simply to maximize summation, let's say I going from 1 up to n, Pi xi, I'm maximizing profit subject to total weight of the knapsack not exceeding W. So what is this doing? Xi is 0, 1. Okay. So whenever you write an integer program, it's important you define what the variable means. So what is x? Essentially, xi takes a value 1 if item I is put in the knapsack, and 0 if you don't put it in. Okay. So this is one of the, if item I is not put in knapsack. So this is one of the basic 0, 1 optimization problems. Okay. So it's quite clear. So whenever xi is 1, I take the profit pi and I use a weight wi. I should ensure I don't put, I would like to put as many items as possible, but I've got a capacity constraint, okay, which is what makes the problem non-trivial. Okay. Okay. So we have seen this problem before, and this should be very straightforward. Okay. It should be quite clear. Okay. So binary decisions is naturally where you'll have integer programming variables. Okay. The second class of, the second thing that you can do with IPs, any questions there with the formulation? Of course, there are also integer versions of the knapsack. So you might have versions where you might have multiple. So this item of type 1, maybe you have got many of them. Okay. So you can decide, for example, to take 5 such items or 4 such items. So if you relax x in 0, 1, n to x in zn plus, for example, that's a general integer knapsack problem. You have multiple, you can take multiple items of the same type. Okay. Okay. So the next thing you can do with binary variables and integer programs is you can model like logical relationship among events. Okay. So basically, binary variables helps you capture logic. Okay. Okay. So you can capture logical relationship among events. So let's say I've got variables. Let's call this xj. Maybe xj is 1 if some event j occurs. Again, think of this as a decision variable. Okay, and 0 otherwise. So if the event does not occur. Okay. So suppose I want to capture a constraint saying exactly one event occurs, or exactly two, let's say exactly two event occurs. Okay. Or let's have exactly one, and I've got n such events. Okay. Exactly one event occurs. How would I model this? I would say x is 0, 1, n, and I would add a single linear constraint that says summation j from 1 up to n, xj is equal to 1. Jointly, this models the fact that exactly one event occurs because the variables are binary and they add up to 1. Exactly one of them has to be 1. Everything else has to be 0. Okay. So the fact that I can model exactly one event happening and the remaining n minus 1 events not happening can be captured using binary variables and a linear constraint. If I want, for example, at most, let's say at most, let's say 5 events occur. How would you model this? X in 0, 1, n. Summation j from 1 up to n, xj. What will you do? At most 5, less than equal to 5. The sums of the x's cannot exceed 5. So I can have maybe 0 events occurring, 1 event occurring, 2, 3, 4, 5. As the x's changes, they can never add up more than 5. All possible combinations of 5 events or less occurring will be captured by this set. Okay. So a lot of logical things can be captured uh, among events can be captured. Okay. So another example is, so let's say I've got so let's say I've got a constraint of the following type. If one event occurs, then uh, another event occurs. So I'm talking now about, let's say, two events or two variables. Okay, so let's say I've got x, which is binary, and y, which is binary. So I've got two events. Okay, when x is 1, the first event occurs, and 0, it does not occur. If y is 1, the second event occurs. Otherwise, it does not occur. Okay. So I want to capture the fact when x is, so what am I trying to capture here? I'm trying to capture the implication that x is equal to 1. So if the first event occurs, then I want to capture the fact that y has to be 1. This is what this constraint is saying. If one event occurs, the other event has to occur. How would I capture this? I would capture this logical constraint by saying x and y have to be binary, and what would we do? We would have a constraint saying x greater than equal to, less than equal to y. What does this do? If x is 1, it forces y to be 1. The other way you can think about this is if y is equal to 0, x has to be 0, the contra. Okay. If y is 0, x has to be 0. This is what this captures. Okay. This is a linear constraint with two binary variables. Okay. So this set captures this particular condition. Okay. So I'll show you an example of how you can use this. Is that clear? And you can do basically many such logical implications with binary variables and linear constraints. So here's one class of problems, what are called facility location. And we will look at a version of this problem. Okay. So here's an example. So I've got a set of a set of, let's say, facilities. Okay. So facilities are like, think of these as locations where you are trying to open factories. Okay. And you've got a set of clients. Okay. So let's say I've got M facilities and I've got N clients that I want to serve. Okay. So facilities are trying to serve clients. So you're trying to produce in these facilities to serve the clients, N of them. Okay. So there are many versions of the facility location problem. I'll give you some, I'll tell you one version here. Okay. So what is the problem? So the problem is you have essentially, so M facilities, N clients, there is a fixed cost for opening a facility. So if I decide to open a facility, I'll pay a fixed cost. Let's call it FI, fixed cost of opening facility I. Okay. And this goes for, of course, I can take values, opening facility I for I going from 1 up to M. So I have to decide, should I open a factory here or no? So think of a planning problem. You decide, do you have to open a factory in this location or no? You've got a potential set of places you have decided. If you decide to open in a particular place, you pay some fixed cost, which is FI. Okay. Once you decide to open a facility, there's a cost allotted with serving a client with a facility. So if I take facility I and client J, the cost of serving client J with facility I is CIJ. Okay. So CIJ is the cost of serving client J with facility I. Okay. And so you can serve uh, clients with any number of facilities, and the only condition that we will have is, so in this facility location problem, each client can be served by one facility. Okay, so basically, so in this version of the problem, I have to figure out for every client which facility is going to serve them. So let's say I've got people in this, so I've got a client sitting in this region. Which of my facilities is going to serve them? I've got clients in some other location. Among all the facilities I've opened, which facility is going to serve them? Okay, so this is a specification in the problem. Okay, I mean, you can have other versions of the problem when clients might be served by multiple facilities and you decide how much to produce at each spot. But in this version of the problem, we are going to just, every client will be served by one facility. Okay, so that's the problem. Is the setup clear? Again, facility location, there are books just written on this class of problems, facility location. There are full books on this. Okay. Okay. So what do you do here? You need to first define variables. Okay. So the variables are, there are going to be two types of variables. You have to decide where you have to open, which facilities you have to open. Okay. And that's a choice. You have to decide to open a facility or no, build a factory or no. Okay. So that's going to be a binary variable, yi. One, if facility I is opened. Zero, otherwise. What does otherwise mean? You do not open facility I. Okay. If facility I is not opened or not built. Okay. That's one variable. I have to decide y1 up to ym to figure out which facilities have to open. And then I have to figure out an assignment problem. I have to figure out which facility will serve which client. There are two problems, two steps here. First, you have to decide which ones to open. Once you decide which facilities to open, you have to then figure out, if you open 5 facilities, which among these 5 will serve each of the clients. Okay. So my second set of variables is xij is, it's again in this problem, it's a 0-1 problem, because in this problem, I'm not having demand at locations. Okay. I'm just thinking of a binary allocation problem here. So it's a high level decision. Okay. So in this problem, xij is 1 if facility I serves client J, 0 otherwise. That means facility I does not serve client J. So I've got two sets of variables. Of course, I goes from 1 up to M. Here I goes from 1 up to M and J goes from 1 up to N. Okay. So I've got yi variables are here and the xij variables on this. Okay. So let's write down the optimization problem. I want to minimize total two types of costs. Cost of opening facilities cost of serving clients by facilities. So I want to minimize summation I going from 1 up to m FIYI plus summation I going from 1 up to m j going from 1 up to n Cij Xij. Every time I pick up either 1 or 1, I have a fixed cost. Xij is 1. I pick up the cost of serving client j with facility I. And these are all linear costs, basically, in terms of the variables x's and y's. That's a linear function. Subject to what are my constraints? First constraint, yi has to be 0, 1 for I going from 1 up to m. Xij has to be 0, 1 for I going from 1 up to m, j going from 1 up to n. N clients, m facilities. Okay. So what are my other constraints I require? So one constraint I require is each client can be served by one facility. So if I look at any particular client, Xij's are binary. I want it to be served by one facility. This is exactly one event occurs. I require at every j, exactly one of the Xij's has to equal to 1. So at location 1, at most, at client 1, at most one of these Xij's has to be equal to 1, right? So I will have one constraint, which is saying summation Xij sum across all facilities has to equal to 1 for j going from 1 up to n. So every facility, every client, exactly one of the Xij's will add up to 1 across all I, because X's are binary, so exactly 1 will be forced to 1. Okay. We're still not done, because what is missing? In this formulation, what is missing right now is the connection between X and Y. How are X and Y related to each other? Right now, if you look at this optimization problem, X's are together. That is, these constraints only involve X. This constraint only involves Y. There is no link between X and Y. That means you're missing something in your optimization problem, which has to link up these two sets of variables. What is that constraint? Xij, if yi is 0, every Xij has to be 0. Or if Xij, if any one Xij is 1, the corresponding yi better be 1. This is this constraint. If any one of the Xij's is equal to 1, yi better be 1. You cannot serve a client with a facility if the facility is not opened. You have to pay the fixed cost. So what is that constraint? It exactly says Xij is less than equal to yi for every I from 1 up to m and j from 1 up to n. This constraint is what links up the x and the y variables. Without this, the problem is just separable. And it's not interesting. Okay. So again, this is exactly capturing the fact. What is this logical constraint capturing? If Xij is, any one Xij is 1, the corresponding yi has to become 1. Or equivalently, if any one yi is 0, all the Xij's coming out of that yi have to be 0 because of the binary constraints. So you can see the modeling power of integer variables with linear constraints. It captures logical implications, which is one of the important things with integer programming. It can capture logic, which is harder to do with linear programming. Linear programming, everything is continuous. Okay. Of course, that comes with the benefits. Okay, we'll come back to that later. Okay. Okay. Any questions with this formulation? In fact, actually, this is what is called a disaggregated formulation. Don't worry about it right now. Later on, we will talk about an alternative formulation for the same problem. Okay. Any questions with this so far? Okay. So, so if you sort of, you can generalize this idea. Okay. And basically, if you have fixed costs or fixed costs, fixed charge. Okay. So in the previous problem, I just did it with, there were just binary variables here in this example. There was a fixed cost already in this example. But essentially, in this case, I was just producing, I was allocating, once a facility was opened, I'm just allocating the facility to a client. Okay. If you have a production quantity, so for example, suppose I'm producing some amount, let's say X greater than 0 is some production amount. And let's say Y is 0 or 1. If you produce a positive amount, so the so you can capture the notion of fixed cost basically with this binary variables. Positive, if you produce a positive amount quantity and 0 otherwise. So what is a fixed cost problem? Basically, it's a problem where you want to model cost of the following type. If you decide not to produce anything, if X is 0, you decide to produce nothing. You want the cost to be 0. If you decide to produce some quantity, let's say X is strictly positive, you might want to play a fixed cost of F, and maybe you have some variable costs. Okay, so you can also bring in variable costs if you want to. Okay, but for now, let's just focus on the fixed cost example. Okay, so what is this function capturing? When X is positive, I'm paying a fixed cost of F, but when X is 0, I'm paying a cost of 0. So there is discontinuity in this function. This function is discontinuous at 0. There's a breakpoint here. Okay. The function close to 0 doesn't look, uh, this function is discontinuous because at 0, the way the function behaves has nothing to do with how it behaves close to 0. It's a discontinuous function, but this can be modeled with integer variables. Okay. So all you will have to do is, how can you model something like this? If you're trying to in your optimization problem model something of this type. So to model this, okay, all you have to do is you can add in a constraint of the following type. Okay, X greater less X is some production quantity, but now for the upper bound, so previously I was just choosing to serve, so Xij was a 0, 1 variable, but now X is a production quantity. So all I have to do now is I need to put an upper bound here, some big number M. Okay. So M is a large positive number. Okay. Which you can, in some problems, it's basically like, if your plant, you're producing some items, maybe your plant cannot produce more than 100,000 items. Okay. So then M is 100,000. Okay. Otherwise, you just put some artificial number with very high number, 10 to the power 10. Okay. Of course, it has some effect on the algorithm itself, but basically, M is some large positive number fixed. Okay. Which you can typically find from your problem context. Okay. So what will this do? When when Y is 0, X will be 0. When Y is 1, X can be any number from 0 to M. Okay. And what you will do is you will add in the objective. So add in the cost function, add an objective um, plus F times Y to minimize in cost. Okay. So let's think what will happen. Okay. So this is a constraint I will add, and I will modify my objective, whatever my optimization problem is. If it's a minimization problem, I'll add f times y. If it's a maximization problem, I'll subtract f of y. Okay. What will this do? Okay. When um, um, y is 0, it will force x to be 0 from this constraint. And of course, x is, sorry, I should have said here, y is binary. All of this works because y is binary. Okay. So when y is 0, x has to be 0. When y is 1, okay, what will this do? Essentially, it will let x be any number from 0 to m. It will let me choose whatever I want. Okay. Of course, if x is positive, y will be positive. Okay. Uh, um, if x is strictly positive, y has to be strictly positive. Okay. And let's say um, in my when let's say x was 0 in this problem. Okay. Let's say I'm solving an optimization problem, and let's say x is 0 in the optimal solution. I decide not to produce anything. Because I'm adding f times y to the objective, okay, and I'm going to try to minimize costs, it will force y to be 0 because I'm minimizing costs, right? Y can be any number. I mean, if x is 0 in this implication, y can be what? Y can be 0 or 1. It doesn't matter. Both are valid. But because I'm trying to minimize cost, it will force y to be 0. There's no reason for me to make y 1 in the optimal solution. I'm minimizing costs, right? So by this modification will simply, when x is 0, y star will be 0 due to the objective. Okay, so it's capturing the effect that you want basically. Essentially, when x is strictly positive, y has to be strictly positive. You have to pay the fixed cost. When x is 0, okay, also this will actually work because x is 0, y can be both 0 or 1 from the constraints. But because I'm adding fy to the objective and I'm minimizing cost, it will force y to be 0. It can never be optimal to make y 1. Okay, is that clear? Okay. So you have to check the logic, okay, when you're formulating IPs. So an example of this where you can use this is we have seen lot sizing, dynamic lot sizing. What I showed you of dynamic lot sizing without capacity constraints. But if you have uh, capacity constraints, you can write it as an IP. Okay. So what is capacity constraints? So remember in dynamic lot sizing, there are two types of costs, right? You are, if you remember the problem, what are you doing in lot sizing? You have a set of time periods. Hopefully, you remember the problem. You have demand in each time period. You are deciding in each time period to produce in that time period or carry inventory from the earlier time period to satisfy demand. Okay. I showed you problems. Um, I showed you problems where um, you have capacity constraints. So you have so what happens in this? And every time period, if you produce, you pay. So if you remember the lot sizing problem or no? I hope you remember. There is a production cost, CT, there is an inventory carrying cost, HT, there is a fixed cost of producing any time period, FT, fixed cost, variable cost of production, inventory carrying cost, and maybe you've got capacity constraints too, which means that you cannot produce too much, or you cannot carry too much inventory. You don't have too much storage capacity. So this you can write as an IP. Okay, how? You will minimize total production fixed costs, variable production costs, inventory carrying costs. Okay. The indexing here is just that you don't carry inventory after the last period and so on. What do you have in this problem? You have flow conservation constraints. Essentially, any time period, the flow, the inventory coming in time period T, plus the amount you produce in time period T is the inventory going out of time period T plus the demand. This is flow conservation. Okay. Starting inventory is zero, ending inventory is zero. All this we have done before. Okay. In this problem, there's a fixed cost. So YT is binary. Now it turns out without, even if you have fixed costs, I showed you earlier, you can solve a shortest path problem. So even if you have fixed costs, even if you only have FT, CT, and HT, lot sizing can be solved as a shortest path problem because we can reformulate a new network. But if you have capacity constraints, like I can't produce too much. So for example, I've got constraints of the type XT is I can't produce more than some number. Okay. So when YT is zero, I cannot produce. If I do a fixed, if I allow you to produce in time period T, I've got a capacity UT. So that's a capacity. Okay. So if you've got capacity constraints, and of course XT is non-negative, inventory is non-negative. Okay. And maybe you also, I mean, you might also have inventory carrying, you might also have constraints on the inventory. Maybe the inventory is not too large. But if you have got capacity constraints, basically, I mean, the point here is that if you have capacity constraints, which are these constraints, we didn't have these constraints before. When I did lot sizing earlier, I didn't have these constraints. I only had these constraints, and I basically told you can solve a shortest path problem. But if you have got capacity constraints, you'll have to solve it as an integer program. So sometimes you might have a problem and you add in some additional features, the problem will get more complicated. Okay, and you might have to change your artillery or your tools to deal with. Okay, is that clear? And is it clear what this constraint is doing? UT is a capacity, how much you can produce in time period T. If you don't produce in time period T, you pay a cost of, you cannot produce in a time period. If you produce in time period T, you get a fixed cost of FT. Okay. And if XT was zero, no, you will make YT zero, so minimizing costs. Yeah. Any questions? So the claim is lot sizing with capacity is a, so okay, by the way, in this problem, Y are 0, 1 variables, X and uh, I inventory are continuous variables in this example. Okay. So actually, if you look at what exactly this class of problem is what is a mixed 0, 1 LP problem. I mean, if there are binary variables. Mixed simply means that there are some continuous variables, and every constraint here is linear except for the integrality part, the binary part. Okay. Any questions with these ideas so far? Okay. I'll do one more example and one more idea, and then we can take a break. So one useful thing, of course, with integrality is you can capture discontinuous values of variables. Okay. I mean, clearly, if you just think about integrality, by definition, is discontinuous, right? If I say x is integer, what does it mean? It means x can only take these numbers, integer values, which is a discontinuous set. It's not a continuous set. Okay. I mean, there's no notion of continuity because it's these things don't connect to each other. Okay. Okay. But more generally, suppose I tell you I've got a variable x. Let's say maybe x takes a maybe it's not, maybe x takes values in an interval, but these intervals are disjoint. Okay. So what I mean by this is, let's say x takes values, let's say between L1 and U1, or L2 and U2, or let's say LT and UT, LT and UT, where the intervals are disjoint. Okay, so let's say I've got a variable. Okay, let's look at how this looks like. So I'm looking at this for a single variable. I've got a variable x which takes values between L1 and U1. Okay, if I've got only this constraint, that's a linear constraint, x below U1 and x greater than L1. I can capture this using linear programming. But now I've got x taking values between L1, U1, maybe L2 and U2, maybe L3 and U3, and so on. Okay, so the point here is x can only take these values, and x cannot take values outside these sets. Okay, so somehow I want to capture in my problem that numbers can be between these or these or these sets, but it cannot be anywhere else. Okay, so this can be beautifully captured using integer programming too. Okay, how do you capture this? You will define, you will do the most natural thing, which is to define a binary variable for each interval. Okay, so what we will do is we will define, so define yt to be 1 if, this is my interpretation, if x lies between LT and UT, I want y to take a value 1, 0. Otherwise, that means x doesn't take values in this set. Okay. So now how would we capture it? So how many variables do I have? If I've got, let's say, x taking capital T possible intervals. So in this example, so what I've shown you here is t equal to 3. Okay. But in general, there'll be t such variables, t going from 1 up to capital T, depending on how many intervals I take. Okay. So what do you want to do? X. So for every interval, so okay, so here is the, so we can model it as follows. So we can model this, we can model star as follows. So this is my interpretation of my decision variable yt. So all I'll do is I'll say yt is 0 or 1 for t going from 1 up to capital T. I will define a variable for each interval. Okay. So I'll define a variable here x1, x2, x3 up to xt. Okay. So this variable xt will take numbers between LT of yt and ut of yt. Okay. What do you think this will do? When yt is 0, it will force lower and upper bounds to be 0. So it will force xt to be 0. If yt is 1, it will force xt to take numbers between lt and ut. For t going from 1 up to capital T, I require x to lie in exactly one of these intervals, which means that I require the sum of yt from t going from 1 up to capital T to be 1. This will force exactly one of these y. So there's a y1 here, there's a y2 here. It will force exactly one of them to be 1. Whichever is 1, the corresponding xt will lie between lt and ut. So all I have to do is I can write x as the sum of xt's, and I'm done. With this, every x which lies in the set is exactly a x in one of these intervals. So it exactly satisfies star. This is a reformulation of this condition of star. Every x in this set, sorry, every x in this set every x in this set star is captured in this part, and this is an equivalent reformulation. Okay. linear, 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 binary. So this is a formulation of an integer feasibility problem. Okay. So, so this is a mixed 0 and LP. So for example, suppose I want a decision variable X, let's say to take some numbers. Okay. Let's say X takes numbers 10, 100. Let's say I've got some variable like this, which takes 5 values. It can only take 5 different values. Okay. One way you can model this is very simple. You can simply say X is equal to 10y1 plus 100y2 plus 1000y3 plus 10 to the power 4y4 plus 10 to the power 5y5. So I'm doing the same trick where y1 up to y5 are binary and they add up to 1. y1 to y5 add up to 1. So for example, if this interval L and the upper and lower bounds are the same, it basically captures discontinuous just values of x's. So in this example, I just have a binary variable for each value that x can take. It turns on if y1 is 1, x will become 10. If y3 is 1, x will become 1000 and so on. So you can model discontinuous values for the decision variables using integer programming. Okay. Any questions? Okay, it's 10:55. Let's take a break. When we come back, I'll do a few more examples like this. Okay. But what I want to show you is just the power of modeling with IPs. It's extremely powerful as a modeling technique. Okay, shall we start? 7 minutes out. Okay. So I want to continue with this, just show you a few more examples where you can model things with IPs. So next class of problems that you can model with IPs is piecewise linear functions. Okay. Okay. So first thing you should remember is we have seen piecewise linear convex problems, right? We have seen optimization problems where we are trying to minimize piecewise linear convex functions, and we saw that we can solve those as LPs. So if you're trying to minimize functions like this, we have seen tricks to do this early on, how to model these things using LPs. The difference here is I'm not now just interested in the class of piecewise linear convex functions. I'm interested more broadly in any piecewise linear function. Okay. So of course, there's a much, much larger class of functions. Okay. So let's say I've got a function which maybe looks like this. Okay. So this is clearly not piecewise linear convex, but it's piecewise linear. Okay. So let's say I've got a variable x. Okay. And let's say I've got, so what's a piecewise linear function? One way you can define a piecewise linear function is to take all the points where the linear pieces change. Okay. So in this example, there is, let's say, let me call this maybe A1, A2, these are all the breakpoints, A3, A4, A5, sorry, A6, that's A7, and maybe A8. Maybe my domain is till here, till A8. Okay. And at each of these points, I've got a function value. So if this is x, this is f of x. So at this point, the function value is f of A1, the y coordinate. This is f of A2, and so on and so forth. Okay. And this is f of A8, the height. Okay. So I want to model, let's say I've got an optimization problem where somehow I've got a piecewise linear function that I have to optimize or I have to deal with. Okay. Of course, to find the minimum of a piecewise linear function, all you have to do is you have to actually check all the breakpoints. Okay. But let's say somewhere in the optimization problem, there are multiple piecewise linear functions coming up, and I want to model this. Okay. The tricks of convexity don't work immediately. The question is, how can we model this using IPs, integer programming? Okay. So I'll show you a way to do this. Okay. So we want to model a function f of x which has this structure. Okay. Okay. So the idea is we'll have to create binary variables for every linear piece and then try to set up the logic so that it captures the problem. Okay. And maybe just to keep this, I don't want to make this too big the problem. So maybe let's do this only for from f, just to keep this. Let's do it from A1 to A5. Okay. Just to, let's say my domain is from A1 to A5. So f in this example, so let's say f is in this example, f go the domain of f is from A1 to A5, and it maps to real numbers. Okay. And of course, f is piecewise linear, and clearly it's neither concave nor convex in this example. Okay. So what are we going to do? Okay. So we're going to use, so to model f, we're going to create binary variables. Okay. So the idea is create a binary variable for each piece. Okay. So I'm going to create a binary variable, okay, for each linear piece. So there is one piece here. So how many pieces are there in this example? There is one piece, a second piece, a third piece, and a fourth piece. Okay. So I'm going to create four binary variables. One binary variable per linear piece. Okay. So this is the first linear piece, this is the second linear piece, third linear piece, fourth linear piece. Okay. Okay, so these are going to switch on and off. When it is 1, I want this linear piece to be turned on. When y2 is 1, I want this linear piece to be turned on, and so on. Okay. Okay. The next thing is, for any point in this set, let's say this is the point x. Let's call this point x star. If I want to find f of x star is what? Is given by a convex combination of f of a2 and f of a3. This is the height f of a3, this is the height f of a2. If I can write x star as a convex combination of a2 and a3, just from the equation of a line, I can write down f of x star as a convex combination of a2 and a3. Right? It's a simple formula, basically. Okay. Okay. So we are going. So here are our constraints. Okay. So we want exactly one of the 4 pieces to be turned on. 1, 2, 3, 4. That's captured in this. We are going to have multipliers which are going to tell me the convex combination. So I'm going to have a multiplier. So I've got how many breakpoints? If I've got 4 linear pieces, I'll have 5 breakpoints. Okay. 1, 2, 3, 4, 5. A breakpoint is where the function changes slope. Okay. So I'm going to have a 5 variables which are going to be, basically these variables are going to be they're going to tell me what is my convex combination of the different A's. Okay. So I've got lambda 1 for this point, lambda 2, lambda 3, lambda 4, lambda 5. Okay. Now the key thing is, when I want to write in this example x star, which lies between a2 and a3, I want x star to be written as a convex combination of a2 and a3. So I'll want lambda 2 and lambda 3 to be positive. But I don't want to write, I don't want to find f of x star. I don't want to know anything about f of a1 or f of a5, 4 or a5. This gives me no information. I'm only, the function value at x star is only determined by a2 and a3 and what happens between a2 and a3. Anything away from it, all the other linear pieces tell me no information about what happens at f of x star when x star lies between a2 and a3. So I want all these multipliers, lambda 1, lambda 4, and lambda 5. If there's a multiplier, they have to all be switched off. Okay. They have to be 0. Okay. Okay. At these points. Okay. So how do we do this? So of course, it's a convex combination. So we want these numbers to add up to 1. So here is the key step. So the idea is you have to somehow combine the y and the lambda variables. Okay. So when y1 is 1, lambda 1 and lambda 2 are allowed to be positive. When y2 is 1, lambda 2 and lambda 3 are allowed to be positive. So one way you can capture this is, or the other way to say this is, so I'll show you the constraint. So if lambda 1, for example, is positive, y1 better be positive. If lambda 2 is positive, suppose I choose lambda 2 to be positive, so I'm taking a convex combination which involves a2. Either the first piece or the second piece has to be active. Lambda 3, y2 or y3, lambda 4, y3 or y4. Okay. And lambda 5 only depends on y4. Okay. So let's see what this constraint does. Okay. Okay. So this is clearly the convex combination multipliers. Okay. The problem with this constraint is, when I take a point x star, essentially what can happen? X star can be written as a convex combination of a2 and a3, but x star can also be written as a convex combination of a3 and a1. It can be written as a convex combination of a2 and a5 in this constraint. So I could have made lambda 2 to be positive and lambda 5 to be positive. and I could still satisfy this constraint. But I don't want to take a convex combination of these 2 points and do a linear interpolation here. I don't want to do this. It has nothing to do. It doesn't tell me anything about the problem, the function piece. I only want to ensure x star, lambda 2 and lambda 3, one of them, only both of them can be, I want them to be positive. Okay. So the way that will happen is through this constraint basically. So what will this constraint say? Because exactly one of the linear pieces is optimal. If y2 was 1, what will this constraint say? If y2 is 1, lambda 2 can be positive, is allowed to be positive. If y2 is 1, lambda 3 can be positive. But if y2 is 1, y1 has to be 0, lambda 1 has to be 0. If y2 is 1, lambda y3 and y4 are 0, lambda 4 and lambda 5 have to be 0. So this ensures we are taking a convex combination using only adjacent breakpoints. Okay. And last, what do we have to do? We write the function value, but the function value is easy to write. The function value is nothing but what is f of x at any point. It is, you have to see which of the at this point, if I've got to multiply lambda 2 and lambda 3, it's a linear interpolation. So this, if this is 50%, 50%, this function value will be 50%, 50%. So the multipliers will tell me. So it'll just simply be lambda 1 times f of a1. It's just a convex combination of these values, function values, because it's a linear function, right? What is the beauty of this formulation? Everything here is binary. You have binary variables. Sorry, this should this actually you don't sorry, this should not be 0 1. Huh? It's it's Lagrange, it's convex combinations. Convex combinations will not be binary. It has to be non-negative and add up to 1. Clearly, I can't have lambdas to be, yeah, because I can have points which are between two breakpoints. Okay, so lambdas will not be, for x star cannot be written as, I require lambda 2 and lambda 3 to be positive for x star to be written appropriately. Okay, so these have to be non-negative. These are convex combination multipliers basically. So what is the beauty of this? Binary variables, non-negative variables, linear constraints. That's a 0 1 linear programming problem, mixed 0 1 linear programming problem. So you want to optimize piecewise linear functions. In your optimization problem, you've got somewhere piecewise linear functions showing up. You can basically use integer programming techniques to model it, basically. So you keep everything linear and you add in binary variables and you ensure your logic is airtight, is correct. Okay. Okay. Any questions with this? I know it's the first time you're seeing it. And I know when I first took integer programming, when I first learned IPs, I was trained as an electrical electronics engineer. Okay. So, I was good at doing calculus and all this type of stuff. Integer programming, the techniques are more logic driven. Their techniques are somewhat different. So it takes some time getting used to the way you think about IPs. Okay. Uh, so, uh, so the more you practice with these techniques, the more comfortable you will get with it. Okay. Any questions with this, or is it clear what's happening in this? Is it clear the logic of all these things? Or yeah? Okay. Just shake your head if you understand, that's fine. I don't have to. Yeah, yeah. If you shake your head, I'm okay. Yeah. Okay. So okay, of course, there is some cost in the sense that you are introducing like as many variables as number of pieces, and you are introducing like all these, so you're I mean, you have to bring in, like, in this example, 4 plus 5, 9 variables to capture the fact that you're searching over this entire space from A1 to A5 and to ensure you're doing things correctly with respect to the problem. Okay. Okay. Fine. Good. So let's continue with this. Okay. So the next example is problems where you're doing union of sets, or actually not sets, let's say union of polytopes, or what are called disjunctions. So we have sort of seen an example of this. So we sort of saw an example here. Like this is a union, right? I I am taking, like in this example, they're disjoint sets, and X should be in either this set or this set. Okay. But now we're going to slightly more generalize this. Okay. So let's say, given, so let's say I give you K polytopes, given K polytopes. Okay. So what's a polytope? Of course, it's a polyhedron with boundedness. Okay. So I'm going to describe the conditions only for polytopes for bounded regions. If you have polyhedrons and the unbounded regions, you require some additional conditions. But let's do the case when things are bounded. In most practical applications, you can put some upper bounds on the variables. Okay. Okay. So given K polytopes of the form, let's say Pk is a set, X in Rn. Let's say I've got a constraint Ax greater than Bk. So A is a matrix, B is a vector, and let's say X is bounded. So let's say X lies between some upper and lower bounds, let's say 0 and UK. Okay, let's take this polytope for simplicity. Okay. Okay. And there are K such polytopes. Okay. Okay. Let's say I want to minimize, we want to minimize a linear function over, so we want to minimize a linear function over the union of these sets. So P1 union P2 union P capital K. Okay. So I give you sets. Okay. So let's say I give you a polyhedron. I give you another polyhedron. Maybe I give you a third polyhedron. So this is, let's say this is P1. Let's say this is P2. So maybe let me make this slightly more interesting. The set. Let's say this is P3. Okay. So I've got three polyhedron. Okay. If I say I want to minimize a linear function over the intersection of polyhedron, how will I do that? So if I got convex sets, so forget for now polyhedron. Just think of convex sets. If I give you convex sets and I intersect them, that's also a convex set. Okay. You take the intersection of P1, P2, and P3. What is the intersection? It's precisely the small triangular piece in this middle. That's also a polyhedron. In fact, it's a polytope because everything is bounded. I mean, that's a linear programming feasible region. If I want to minimize over the intersection of sets, all I have to do is, for minimizing over the intersection, all I have to do is minimize C transpose X, just put in each constraint. Just add in all the constraints, ensure all of them are jointly satisfied, and you minimize and you solve a linear programming problem. What is changing in this problem is I am not interested in minimizing over the intersection of these sets, but I'm interested in optimizing over the union of these sets. So what is the union of these sets? So what is the union of these sets? The union of these sets in this example, the feasible region, is all the shaded region. This is P1 union P2 union P3. Is this a convex set? If I look at this region, is it a convex set? If I look at the union, just look at the shaded region. This is not a convex set. You take a point here and take a point here. Points in the middle do not lie in the set. There are points in the middle which don't lie in the set. So this is not a convex set. Okay. So it's definitely not a polyhedral, the set. Okay. But solving this problem actually is not particularly hard. So how can we do this? Okay, there are a couple of ways you can do it. I will show you the IP way, but first I'll show you just think about it intuitively. What would you do if I give you a problem like this? What would you do if I have to solve? If I tell you, can you still solve this problem? What would you do? Any guesses or suggestions? Or if I want to minimize over the union of sets, a simple idea is optimize over each set separately. So optimize. So here is one way to solve it. So one approach is solve k different linear programs and pick the best among them. Okay. So minimize C transpose X subject to AX, AKX greater than equal to BK, XK between UK and 0. Solve this K different times. Okay. Solve the first linear program. What is the first linear program? It's going to optimize over this set. Okay. Let's say I'm minimizing and let's say my objective is increasing in this direction. Let's say C. Okay. The minimum will be this point. Let's say I'm optimizing, next I'll optimize over P2. The minimum will be this point. Optimize over P3. The minimum, I don't know, might be this point. I mean, it doesn't look like a polyhedron, this one. Okay. Let's let's say it's this point. So I've got 1, 2, and 3. Pick the smallest among these three, whichever gives the smallest value, that's this one. So I could solve k different LPs and solve this problem actually. Because the only thing that I'm doing in this step is what? In this approach. Sometimes I'm optimizing over the same space multiple times because when I optimize over P1, I've already looked at this feasible region. When I optimize over P2, I'm also looking at the feasible region. But the advantage is it's a convex set. So it's easy for me to optimize over this. I can use any LP algorithm I like to solve these problems. Okay. Now it turns out another way to solve this is to solve it using integer programming or what's called a disjunctive formulation. Okay. Okay. So is the idea clear or no? Like what's happening here? Yeah. You're looking a little bit, I'm not convinced. Or maybe it's very obvious. It works. This method will work. It will give you the optimal solution. It will work. So it's like, but this is not solving one LP. So there are k different LPs. This is not the same thing as intersecting the LPs and solving it because you see the optimal solution for this problem is actually this point, right? Overall, think about in this example, what is the optimal solution? It's actually this point. If I intersect all the sets, the optimal solution would have been this point, which is not optimal for this problem, for the union. So this method works. It will always work. Okay. Of course, if the number of sets you're optimizing over is very large, there's some challenges, but this method will work. Okay. Okay. There's another approach, but if you want to solve it one shot, not k different times. So think of k being some very large number. Let's say I give you 100 different polytopes. Okay. So to solve 100 different linear programs to solve this problem, can I solve it in one shot? Okay. It turns out you can. Okay. One way to do it is first you can solve it as an integer program. Okay. So let me show you the IP formulation for today. Okay. Which is, so is alternative approach. Alternate approach. We'll use an idea similar to what we did here with the disjunctions, like with the discontinuous values. Okay. We'll try to introduce a variable for each set and then try to ensure we bring them all together. Okay. That's a basic idea. Okay. So what are we going to do? So I'm going to define, so I'm going to have a define a variable, let's say yk to be 1 if kth polytope is chosen and 0 otherwise. Okay. 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 So how will you solve this? So I want to minimize C transpose X. Okay, I've got K different polytopes, right? So I have to either optimize over U1, P1, or P2, or P3, and so on. So so YK is binary. I want to pick one of the K different polytopes. I mean, when I'm optimizing over the union of sets, every point that I get to ultimately will lie in one of the polytopes. Okay, it might lie in the intersection of many of the polytopes, but it definitely lies in one of the polytopes. Okay. So I want to pick at least one of these polytopes. In fact, I want to pick one of these polytopes. Okay, so this is exactly picking one polytope. I want to now capture this idea of the fact that I want a solution for each of the polytopes. How do I do that? Okay. So the idea is A times, I'm going to define a new variable for every polytope. Okay. So I'm defining a new variable xk for each polytope. And I will do what is called this homogenization trick, which is to multiply. So remember, my constraints are Ax greater than or equal to B indexed by K. So I do what is called this homogenization trick. So I basically multiply my right hand side by yk. Okay. Where my xk lies between 0 and I've got an upper bound, it's a polytope, uk times yk for k going from 1 up to k. Okay, let's think about what this is doing. Okay. So what have I done? I've introduced a few new variables. I've got x here. So x, of course, has to be written. X is nothing but just summation of xk's, xk going from 1 up to capital K. Okay, so I can take out the x, I can write everything in terms of xk's basically. Okay. So this constraint is, I mean, you can write x in terms of sums or take out the x here and just write this as, you can take out this constraint and simply write this as C transpose summation K. It's the same thing because there's only one constraint which involves x. Okay. And there's an equality constraint. Okay. Why does this work? Okay. I'm picking one polytope. Okay. So say yk, let's say yk is equal to 1. What does this do? It will force ak xk is greater than bk times yk, which is 1, which is bk. Okay. So xk and the other constraint is xk between 0, uk times 1, which is uk. So what is clear is xk lies in the polytope k, right? Ak times that vector is greater than or equal to bk, and the vector lies between 0 and uk. That's exactly what the definition of the polytope is. So clearly, xk is a point in the polytope. So one yk is 1, but then many of the y's are 0. What happens to the 0 vectors? The y's are 0. So for all other L, where YL is 0, because it's binary, everything else has to be 0. What will happen? You will get what? AL times XL is greater than or equal to BL times 0, which is 0. Okay. So it says A times X is greater than or equal to 0. The addition, in addition, XL is between 0 and UL times YL, which is 0, which is equal to 0. So XL lies between 0 and 0, which means XL is 0. If XL is 0, this constraint is redundant. It is A times 0 is greater than equal to 0, 0 greater than equal to 0. So these are all redundant constraints. They basically just say 0 equal to 0 or 0 greater than equal to 0, which has no important information. Okay. But the important thing here is XL becomes 0. If XL is 0, all the x's are 0. What is my x? Is a summation of all these xk's. Exactly one xk I pick up, everything else is 0. So summation of xl from 1 up to capital K will exactly be equal to xk, which lies in the polyhedron. So I pick up what I wanted. Okay. This trick, the key idea here is this idea of multiplying the right hand side of the vector by yk. Okay. So this is actually called the Balash disjunctive formulation. Okay. Uh, I mean, there are versions of this result, but basically, Egon Balash was a optimizer, discrete optimizer who proposed this in the 70s for disjunctive formulations. It turns out actually in this problem, you can even relax the integrality constraints, the y's between 0, 1. You can relax it to lie between 0 and 1. So you don't have to force y's. I mean, it's very clear when yks are 0 or 1, this thing holds. But when y lies between 0 and 1, so you take the linear relaxation, it's also the LP relaxation will also be tight for this example. Okay. It turns out this is also true, actually. Okay. We won't prove that result at this point, but I'll come back to that later, maybe. But uh, but uh, just a note. Okay. So I mean, just on a side note, I think Egon Balash passed away about 5 years back. About 10 years back, I'd gone for a conference. At that time, he was 95 years old. Okay. And he was talking research at the age of 95. And among all the talks I heard in that conference in terms of plenaries, it was by far the clearest and the most precise. So the point is, people who do research and the people who have worked on some of these things, they're just great minds, basically. If you look at some of their work. So this work has been pretty important. This disjunctive formulation. So it's a useful tool. And in some ways, you might expect that you should be able to solve it potentially as an LP because we're solving k different LPs. So somehow we should be able to aggregate these k different LPs. So the LP relaxation of this problem possibly should be tight, and you can show that basically. Okay. Okay. But at least if you think about integrality, the integral restrictions work here. It captures the formulation. Okay. Okay. Any questions with this idea? Hopefully, I'm convincing you that integer programming has got a lot of modeling power. Okay. Because one of my gripes is that everything is not nonlinear optimization. Okay. Everything is not solving a neural network problem. Okay. Integer programming problems require other techniques. Okay. And so there's a lot of interesting ideas in discrete optimization, which hopefully some of that at least I can expose you to in this course. Okay, fine. So let's continue. Okay. Uh, the seventh idea is products of binary variables. Okay. Okay. So everything so far has been linear and integer variables. But of course, there are problems which are non-linear, and sometimes these things can also be converted. Okay. So the simplest example is if I give you two variables, x1 and x2, both of which are binary. Okay. And let's say somewhere in my optimization problem, I've got constraints which involve the product of x1 and x2. Okay. So what will this variable take? So clearly when x1 and x2 both are 0, y is going to be 0. When any one of them is 0, y is still going to be 0. And if both are 1, y is going to be 1. So that's what's called a truth table. Essentially for every x1 and x2, what is the y values? Okay. Okay. So definitely if I'm having an optimization problem, so let's say here's an optimization problem. So I'll give you an example. So these are what are called, I'll give you just one example. It's called QUBO, quadratic unconstrained binary optimization. Okay. Again, this problem is of a lot of interest. It's a computationally challenging problem, but lot of people in different areas have worked on these classes of problems. Okay. So what is a QUBO? It's basically a problem of the following type. You have got a matrix. So you want to minimize a quadratic function. Okay. So what's a quadratic function? You take X transpose QX. Okay. So Q is a n by n matrix. Okay. It need not have any structure. Of course, it's real valued for problems we are interested in. Okay. Subject to X being in the 0, 1 set. So basically, every xi can take value 0 or 1. I've got n variables. What is the challenge? The number of possible x values is 2 to the power n, right? The number of feasible solutions is 2 to the power n. So if you're going to tell me that you're going to enumerate all solutions and you're going to compute the objective function for each solution, I'm going to tell you bad idea. Okay, because this grows exponentially in n. Okay, so this algorithm will not work as you scale n. Okay, so what do you do? Okay, so this is clearly not in the class of problems we have studied so far, because so far I've told you everything is, I only define problems involving linear functions and linear equations and binary variables. But here it's violating a basic principle, that is, though this is fine, this is quadratic, this is not linear. Okay. Now, there are many ways you can try to tackle this problem. And in fact, many methods have been proposed. But one method is to try to transform it to a linear programming, 0, 1 linear programming problem. And this can be done because in this example, if you look at every term, it's a product of two variables. This quadratic function will have either terms of the type xi squared or xi xj. Okay. So the first thing is, if x1 is 0, 1, what is x1 squared? X1 squared is also 0, 1. In fact, x1 squared is x1. X2 squared is x2 when it is binary. If x takes value 0 or 1, x squared is x. Okay. So whenever, like, at least the terms of there'll be x1 squared terms. The x1 squared terms, forget it, write it as x1. X2 squared terms, write it as x2. Because in this set, if you're optimizing over the hypercube and the extreme points of the hypercube, that is the binary vectors, x squared is x. Okay, but what is not obvious is what you do with the xi, xj terms, the cross terms. Okay. So it turns out you can actually model this also as, so this part is easy. This part, you can model using the following trick. Okay. So this is called the McCormick relaxation. It's called the McCormick. So by the way, all these are names of people who have proposed. Okay. I mean, the names are based on techniques of different people who have proposed it. I'm showing this to you for the binary case, but there are versions of this for general integer cases. But let's take for the binary case. So this is called the McCormick formulation. Okay. Uh, so what is this formulation? What you do is very simple. So you want to capture this set. So I'm interested in capturing this set. Huh? I claim star can be re-expressed in the following way. X1 and x2 have to be binary. Okay, that's obviously needed. But for capturing y, I will do the following. I will write y is x1 and x2, but x1 and x2 are binary, right? So if x2 can either take a value, the maximum value x2 can take is 1. So y can never exceed x1, y can never exceed x2. Okay. Okay. So of course, y also has to be non-negative. Okay. So what will this do? So for example, if you look at this constraint right now, if x1 is, let's say x1 and x2 both are 0, what will this constraint do? It will force y to be 0 because y is less than equal to 0 and y greater than equal to 0. If one of the variables is 0, if let's say x1 is 0, y less than equal to 0, y less than equal to 1, y greater than equal to 0, y has to be 0. If x2 is 0 and x1 is 1, symmetrical argument. Y less than equal to 1, y less than equal to 0. That means y has to be less than equal to 0. Y greater than equal to 0. So y has to be 0. So the only last case you have to worry about is what happens when both are 1. If x1 and x2 both are 1, y is less than equal to 1, y greater than equal to 0. But I want in that case y to be 1. So the way you can capture that is with one additional constraint, which is y greater than equal to x1 plus x2 minus 1. Let's check what happens. When x1 and x2 both are 1, 1 plus 1 minus 1, that's 1. So y less than equal to 1, y greater than equal to 1, y greater than equal to 0, which means y has to be 1. When x1 and x2, let's say both are 0, this is greater than equal, y greater than equal to 0 plus 0 minus 1, which is minus 1. Y greater than equal to 0 will dominate y greater than equal to minus 1. This is a redundant constraint. It adds no value. So this constraint becomes important when both x1 and x2 are 1. But you require to deal with that case because that's when this variable is switching on. So the claim is this is exactly equivalent to this quadratic term, product of binary variables. But these are just linear constraints involving y and x. So I can rewrite a quadratic unconstrained binary optimization problem. So if I take a cubo problem, okay, just for simplicity, let me write this out term by term. So I've got summation I from 1 up to n. Let's say the diagonal entries of the matrix, they will pick up xi squared. The off diagonal entries, I'm going to call them I not equal to j. There are qij terms, xi, xj, subject to x in 0, 1, n. I claim, so this is quadratic still. I claim this can be written as a mixed 0, 1 LP. What do I do? I showed you a trick for one pair of variables. Repeat this for every pair of variables. Define a new variable y for every pair. Okay, so this is the same as minimum. Okay, so the first thing is the quadratic terms on the xi squareds are easy to deal with. I can simply write that as xi because x is 0, 1, n. Okay, so this is okay. So the idea is for every I not equal to j, qij, the xi xj term, I will add in a new variable. Okay. So this is actually what's called a lifting technique, and we will come back to this later. You lift by adding in new variables. Okay, and we'll come back to this. Okay. But you add in new variables and you ensure yij is less than equal to xi, yij is less than equal to xj, yij greater than equal to 0, xi plus xj minus 1. You do this for every I not equal to j. Because you take take x1 and x2, write y1, 2. Take x1 and x3, write y1, 3. Okay. If your matrix is not symmetric, similarly do y2, 1, and so on and so forth. Just so the number of variables here will be roughly, so number of variables, I mean, you can be precise about the number, but essentially it'll be roughly order n squared. Okay. You can calculate it exactly, but basically it's order n squared because you're taking every pair, you have a new variable. Okay. So your original problem was n variables, you went up by n to n squared. Okay. But the idea is why would you want to do this? If I've got a good algorithm for solving integer linear programming, I can go and apply that algorithm to this problem. And I can solve basically the quadratic integer case too. So if I have a good algorithm for this problem, I can basically solve this original problem, which was not originally in this class of problems, but I transformed it. Okay. So this is why transformations are useful, because you can take a class of problems and make them into some other class of problems for which you might have good algorithms. Okay. Of course, this is not the only way people solve this problem. There are many other ways people can solve this problem. But I just wanted to show you that this can also be written as a mixed integer linear program. Okay. Any questions? Okay. Okay. I'm going to show you. So I don't want to do the logic. So I've got one logical constraint, but I won't do that. I won't do that today. I just want to show you one example of a problem. So when you learn integer programming, there are many applications you can think of. So I want to show you one application. Let's see how much we can do. Let me try to show you both the applications. So one thing with integer programming is actually many puzzles or games can be modeled using integer programming. Okay. And I'm just going to show you one example here. But if those of you, if you like puzzles or games or something like that, not everything, but many of those things can be modeled using integer programming. So one example is the following. You're familiar with the game Sudoku, with the puzzles, with this crossword Sudoku? Okay. So I'm going to sort of take the fun out of Sudoku by saying that solving Sudoku is basically solving an integer linear program. Why? So what is Sudoku? So you've got a 9 by 9 grid. Okay. So you've got nine rows to 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So you got 9 rows and you've got 9 columns. In the basic Sudoku, there are extensions of this, but let's do the basic one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. And then you'll have one more column, ninth column. Okay. So it's a 9 by 9 grid. Okay. And what happens in Sudoku? In Sudoku, typically you're given numbers, and not you're typically, you're always given numbers in different elements of the grid. Okay, so maybe you've got a number 1 here. Sorry. Maybe you've got a number 1. Maybe you've got a number 3 here. Maybe you've got a number 2 here. Okay, so you'll have numbers given to you in different parts of the grid. Okay, maybe 3 here, maybe 4. I don't know if you know the rules of Sudoku, but basically, so you're going to have a set of numbers given to you. So I'm going to label I as 1 up to 9, the rows. So this is I. And I'm going to label the columns as J from 1 up to 9. So this is basically a matrix. Okay. So what is the rule of Sudoku? If I give you numbers of this type, okay, I'm just putting in some numbers. Okay. I don't know if this one has a solution or no. Let's say something like this. Okay. What Sudoku says is you have to it's a 9 by 9 grid. You need to fill in the numbers so that every row contains exactly one of each of the 9 numbers, right? So the number 1 has already occurred in row 1. So number 1 cannot occur anymore in row 1. So 2 to 9 have to fill up the others. But when you do this, you'd also ensure along every column, each number comes once. So you cannot put, for example, 4 here because 4 is already along this column. So I have to put 4 maybe here, but I can't put it here. I can put 4 here. Okay. Maybe, but then I have to check other things. Okay. That's the second rule. Third rule is even within the sub blocks, so there are 9 such subblocks. Okay, if you take the 3 by 3 subblocks, within this subblocks, so in this subblock, the number 1 cannot occur again. 1 has already occurred. So number 1 to 9 has to occur once. These are the only rules. There's no other rule for Sudoku. Okay, you have to fill out the table. You're familiar with this game? I mean, some of you are shaking heads. Okay, okay. So I claim that this is an integer feasibility problem. You can write this as an integer linear program, go to your solver and solve it. Okay. Why? Left define variables. So key is to define a variable. And there are different variables you can define. You can define, for example, xij. So, okay. So every cell is indexed by I comma j. Okay. So cell 1, 1 is this. Cell 9 comma 1 is this. Okay. So one way you can define it is you can say I will define a variable xij and I'll tell you what numbers are there in xij. It can be from number 1 up to number 9. This is one variable. Okay. It turns out this is a variable and you probably can write down a formulation with this, but a nicer variable to work with is a variable of the following type, which is I will define, so this is my variable xijk. I'll give a third index where I will let this be 1 if the cell I comma j contains integer k and 0 otherwise. Okay, that's my, so I'm, instead of writing x, so I could have had only 81 variables, right? 9 into 9, 81. There are 81 cells here. So I could have had 81 variables where each variable took 9 different values. But I will make this into 9 into 9 into 9, which is, I guess, 81, 729 variables. Okay. Where each variable now is binary. Okay. So for example, so now I'll say, what is the Sudoku problem? Is it clear what the variables mean? Xij, okay. Okay. So here's a Sudoku problem. So Sudoku as a 0, 1 LP feasibility problem. So there is no notion of optimization here, because what is Sudoku? Sudoku says find a solution, right? That's what Sudoku says. It says try to fill out the grid. So find me a feasible solution. There's no notion of cost. Okay. So it's a feasibility problem. So it's like minimizing 0 objective. They find me a feasible solution. Okay. So what are the constraints? Okay. So first is xijk is binary. Okay. For every I, j, and k. Okay. And by the way, all of these go from 1 up to 9. Okay. So the indices here are I goes from 1 to 9, j goes from 1 to 9, k goes from 1 to 9. Okay. Now let's take the row constraint. What should the row constraint tell me? It should tell me that along the row, every integer has to occur once. So the row constraint will be you add up along every, so the number 1 can occur only once along this row. Okay. So if you sum up x, I, j, k, you sum this up over every j from 1 up to 9, this should be equal to 1 for every I, for every k. Okay. Okay. So for example, let's take row 9. Okay. Let's take row 9. So let's say I is 9. Let's say I is 9. Okay. I is equal to 9. Let's take the number 2. The number 2 can only come once on this row, right? So what is this constraint telling me? So when I is 9 and k is 2, what is this constraint telling me? X, 9, 1, j can go from 1 to 9. When j goes from 1 to 9 means I'm taking all the elements along this row, right? So I'll call this row, okay? I'm taking all the elements along this row and I want to make that equal to 1. Because all of these are binary, only one of them can be 1. So the number, only one of these rows, sorry, only one of these cells can have x, 9, j, comma 2 to be 1 because they add up to 1. Is that clear? Similarly, I can do it for column. Summation I going from 1 up to 9 along a particular column, xijk equal to 1 for every j from 1 to 9, k from 1 to 9. Okay. So for example, x111 plus x121 plus x131 plus x141 plus x151 all the way up to x191 equals to 1. Which one of them has to become 1, which means wherever that xij, whichever entry, wherever that one is, that number is 1, that's where I'll put the number 1. The third is for these sub blocks. Okay. So you have to just index this carefully, but you can do a similar thing for every I and j in a sub block. Okay. And you can do this carefully with indexing. Sub blocks for all k. So what do I mean by this sub block? I mean, let's take the number, uh, let's take the number, let's say 2. Sorry, I'm trying to use a color. Let's take the number 2, for example. Okay. The number 2 can occur only once in this block. How will I write that constraint? I'll write that as, I'll just show you one constraint of the type. It'll be simple. It'll be x 1, 1, 2 plus x 1, 2, 2 plus x 1, 3, 2. That's these three cells plus x 2, 1, 2, 2, 1 plus x 2, 2, 2 plus x 2, 3, 2 plus x 3, 1, 2 plus x 3, 2, 2 plus x 3, 3, 2 equal to 1. What is this saying? It's basically counting all these cells and saying the number the number 2 has to occur once because all of these are binary. So somewhere the number 2 has to be put in. That is this constraint. You do this for every block, for every number. That's the third rule of Sudoku. There are these three rules basically. Okay. Okay. Of course, every cell can have only one number, right? So the sum of xijk for all k should be equal to 1 for every I and j, right? Every cell can have only one number. Don't give me a solution where one cell has two numbers. Huh? So then if I put a number, uh, let's say 2 here, I cannot put any other number here. That's captured by this constraint. And what is the last part of this Sudoku problem? What is the original puzzle given to you? The original puzzle given to you forces some of these numbers fixed. So for example, in this Sudoku puzzle, x1, 8, 1, in this Sudoku puzzle, x181 is equal to 1. Why? The first row, eighth column is set to be 1. In this Sudoku puzzle, the first row, third column has the number 4. That is just x134 equal to 1. All of these are just, again, linear constraints which capture the starting board. Okay. You solve this you solve this integer constraints. You find me a feasible solution to these integer problem. I solve Sudoku. If you cannot find me a solution to this problem, that Sudoku has no solution. Okay. So we have algorithmized Sudoku basically. So if you have an integer programming solver, and I've actually written this code down before, you can. It's very easy to write. Okay, take your solver and just write down the constraints, and you can solve Sudoku basically. Of course, it takes the fun out of the puzzle solving game. But does the Sudoku have a solution or no? It can be found using this by solving uh, a set of linear constraints and integer variables. Okay. Okay. Let's stop here. Next class, I will continue and I will discuss, finish up with formulations, and then the following 2 weeks we'll talk about techniques for solving integer programs. Let's stop today. Homework is due today. Okay, so ensure you pass it back to me by this evening. The last homework also I've uploaded today. It will be related to integer programming. It is due on week 12 on the Friday. Okay, I've uploaded it online. You should be able to start solving it by end of this week. Most of the questions you can try to solve it. Let's stop. No objective. What is Sudoku saying? Sudoku saying just solve. Think of a person solving a puzzle. A person who solves a puzzle just solves a puzzle. They just find a solution. So that is no objective. So there's a feasibility problem. That is no objective. Yeah. Of course, sometimes the Sudokus are well developed. I mean, most Sudokus have a unique solution. So it might be that the Sudoku has only one solution to the problem. Of course, if the Sudoku is very sparse, there might be multiple solutions. But most times, people who develop the Sudoku games, this is not about designing the game. This is about finding the solution. Designing the game means that you want to populate these cells so that maybe there's only one feasible solution, right? So those are other problems basically. But this question is just, I give you a Sudoku problem and I tell you you want to solve Sudoku. So you can do whatever heuristics you like and if you're good at solving Sudokus, but you can give me that problem and I can take it to a computer. I will solve this integer programming problem, feasibility problem, use any integer programming solver. It will give me a solution if it is got one. So there is no objective.